Hi, everyone. Thank you for joining us today. It is 11 o'clock on the hour. Thanks for joining so far. I know we have a couple more people coming in. My name is Ashley Zook, and I'm the National Channel Manager here at Donaldson Company. I work specifically with engineering firms across the United States. And one of the many ways that I help is by setting up lunch and learns. And we were going to get into our webinar today. The purpose of today's webinar is to review the objectives of dust collection system design as it pertains to school woodworking or welding programs. We can also help with other applications as well, as paint booths like wood shops and welding programs tend to be the most typical for schools. Then we're going to discuss the 4 primary components for system design, including some common mistakes that we see, and then we'll answer your question. Just a heads up, it takes years of education experience to become an expert in dust collection system design. The goal of the session today is to give you a brief overview of the basics of school wood shops and welding programs. In case anyone here isn't familiar with Donaldson Company, we have been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the first filter for a tractor engine. Today, we are one of the largest providers of unique filtration technologies, and we excel at producing high quality filters and parts. We pride ourselves with having a global reach with a local touch. Our world headquarters is here in Bloomington, Minnesota, and we have 55 manufacturing plants and 21 distribution centers around the world to support our customers. Before I introduce Dave, I wanted to quickly explain how to engage with us. As you think of questions throughout the webinar, please type them in the chat box and Dave will answer them towards the end of the session. If you need to jump off early, don't worry. I'll reach out to make sure you have all your questions were answered. And then during the webinar, Dave will ask you some questions, and you can use the thumbs up and thumbs down by clicking on the little face icon at the bottom of the screen. And with that, I am pleased to introduce our featured speaker today, Dave Dacona. He is a territory manager with our industrial air filtration unit. He is located in Watertown, Wisconsin. Dave has been with Donaldson for 29 years, covering central and northern Wisconsin and the Upper Peninsula of Michigan, serving customers with system design and problem solving in dust collection industry. He has a background in the fire service, being a captain on a voluntary fire department for the last 16 years and the platoon leader and training officer for the Dodge County Hazmat team. He has his bachelor's degree from the University of Wisconsin, Platteville in industrial technology. Take it away, Dave.
Thank you, Ashley. We'd like to start out by asking about your experience with designing dust collection systems for schools, wood shops, weld shops, and whatever. So, as Ashley said, please use the chat box and type in the letter that best aligns you to the level of experience that you have.
All right, we're getting some answers in here. It looks like we got quite a few C's, a lot of C's, some D's, a couple E's, and a couple A's here. So it looks like we have a little bit of everything. Oh, they're flowing in. A lot of C's, though.
Okay, so a lot of average industrial exposure to this. That's great. That's great. So hopefully this presentation will have some benefit for you guys today. So first of all, let's talk a little bit about wood dust and weld fume generated in schools. That's the whole presentation here. There are a lot of important reasons to control the dust generated in school wood shops and fume generated in school weld shops. I mean, such as improving air quality for the students and staff, for exposure control, like reducing potential dust in the breathing zones of the students operating the process. There's environmental concerns like EPA standards for outdoor exhausted environmental air quality and outlet emissions requirements. There's also safety concerns, NFPA guidelines for fire and explosion mitigation, and there's also cleanliness, concerns about overall cleanliness of the woodworking, and welding facilities in the school. Now, weld fume, because the way it is produced is very, very small. It's submicron in size. So if you would need a microscope to really see it. There are 4 main types of welding. There's gas tungsten arc or TIG welding. There's shielded metal arc, which is a manual arc welding process. There's gas metal arc or MIG welding, and of course, flux core arc. I did want to point out that if a school woodworking It has other metalworking applications such as CNC machines, a plasma cutting, laser table, or 3D printers, which are all pretty cool these days. We also have product to provide solutions for those as well. Now, you might be wondering what is exactly in weld fume. As you can see by this chart here, there's metals that are being administered on there for the welding: zinc, cadmium, aluminum, all which can be hazardous. And the gases which shield that process, which are argon, helium, nitrogen, carbon dioxide, they all play a part in the welding process. Now, this is what you'll find on every box of welding consumables. Because most weld fume is hazardous, exposure limits are regulated by OSHA and also the EPA if vented outdoors. Now at Donaldson, we define these three classes of dust from woodworking processes based on how their characteristics will impact the selection and style and size of filtration devices best suited to handle them. We define class 1 as a light and fine dust, kind of like generated from sanding dust. There's class 2, which is a medium-sized dust, such as generated from saws, routers, and joiners. And of course, class 3 is the larger sized dust, such as dust generated from planers, edge banders, and lathes, which is being shown in this video. It's generated quite a bit of large dust. Now moving on. There is one important thing to consider for both school wood and weld shops, which is managing combustible risks. When a combustible dust encounters an ignition source, there is a potential for a fire, a flash fire, or an explosion. If the fine particulate is combustible and it mixes with air, like the airflow coming from the dust collector, and there is an ignition source, it can result in a fire. If you add the dispersion of dust, which is frequently by a pulse cleaning collector, you could have a flash fire. And if you add the confinement of the dust, which is the dust collector housing, you could have an explosion. I'm not going to spend a lot of time on this since it is a very complex issue, but I will circle back towards it at the end of the session. But for now, know if there's dust is combustible, there needs to be a mitigation plan in place to protect students, staff, and property. All right, let's talk about the basics of dust collection systems for both wood and weld shops. Now here's a diagram of a typical dust collection system. A blower or fan, you see there, creates airflow, which is used to capture dirty air with a hood, and then conveyed the material through a series of ducts to a dust collector. Here the contaminated is separated out and the clean air passes through the filter media to the fan and where it is discharged to atmosphere. These systems are some of the individual parts that are designed based on characteristics of the dust or fume and various application factors. If one component is poorly designed, the whole system is affected. In system design, we have two main objectives, which we want to accurately predict. We want the air volume in CFM, which is required to effectively capture and control contaminant at the point of generation, and a total energy and horsepower required to produce those airflows. The publication shown here is the Industrial Ventilation Guide, which is an indispensable resource for proper system design. The vent manual is written by the American Conference of Government Industrial Hygienists, or they called the ACGIH, which is a nonprofit scientific organization that advances occupation and environmental health. They offer multiple courses throughout the year on system design using the Vent Guide as its textbook. I myself have attended courses in Michigan and in Alabama to develop my system design expertise and a few of our experts here at Donaldson are actually instructors at this event. If you have any interest in developing your system design knowledge, I do highly recommend taking one of these courses. The ACGIH guidelines are considered by most of the industries, including OSHA, as a standard for proper ventilation design. Now back to our system. The first component that we're going to discuss today is the hood. This is a critical component of the system design that will allow the contaminant and the collection of this fugitive dust. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it is released, while minimizing the energy required to do this. When it comes to assessing an existing system, a few common mistakes that I see are the wrong style hoods are being used. Maybe the hood is not located in an effective position, or we have inadequate airflow at that hood. Okay, as you see here, the most common hood styles used in school projects is a close capturing hood, which relies in establishing a general airflow pattern into the hood, opening to produce a capture velocity at a specific distance from the hood. There are 5 main types of capturing hoods, which are shown here. There's the raw edge hood, the flanged hood, a tapered hood, there's a bell mouth hood, and a slotted hood. Okay, so would you please use the chat box and let me know the most common types of capture hoods that you've specifically used in dust collection systems?
All right, it looks like we got some tapered, a couple bell, some slotted, a lot of taper and slotted.
Tapered and slotted? Okay, very common in these process stuff. That is
Mhm.
awesome. So you guys are familiar with them. So for weld fume, you may see large booths like this, often with curtains for weld stations. We do a lot of testing at Donaldson, so we thought it would be fun to show you a few test videos of our fume hoods. The video in the middle is using a small smoke machine, which a hood is being tested in the lab. The video on the right is a more realistic scenario where a small amount of fume are being emitted and cleared out of there. Now, extraction arms with a bell mouth hood on the end are another good solution for small weld applications for those found in schools. They come in various lengths and diameters. The picture on the right was taken prior to the curtains being installed, and each extraction arm is where a different weld station would be located. Source capture, the weld fume versus ambiently. Now, regardless of the style hood, to be effective, a hood must be positioned properly relative to the point where the contaminant is emitted. Remember, the first objective in hood design is to minimize the air volume required to maintain capture efficiency. To minimize air volume, the hood must be close capture point without disrupting the process. However, it can't reach out to control contaminants far away from the inlet. Consider a vacuum like in your house. To pick up the debris from the surface, the vacuum head must be close to the contaminant or it has no effect. Same thing with a bell housing hood. A hood positioned twice the distance from the generation point rather than the capture point will need to draw approximately 4 times the amount of air to produce the same capture efficiency. And more air means larger collection equipment, larger ducts, larger fans, and more horsepower, all which adds to the capital and operational cost. The square of the distance is a CFM. So a unit 2 foot farther away is 2 squared or 4 times. A hood that's 3 foot away is 3 squared or 9 times the CFM. So you can see where you need to locate that properly. Okay, when determining the required airflow at the hood, the main design factor is called capture velocity. This is the velocity required at the point where contaminated is generated in order to gain control of the contaminant and direct it into the hood. For schools, wood shops' capture velocity is typically about 300 feet per minute, or FPM, although it depends on the application and the style of hood, though. Now, for school weld shops, it is generally between 100 and 250 feet per minute. So when you're designing hoods, you want to avoid airflow extremes. Too much airflow at the hood or pickup point may mean you're picking up good rather than just the nuisance dust. It could also increase your risk of capturing unwanted particulate like sparks and embers. And since more energy is required to move more air, this could also lead to a higher than expected operational costs. Influencing air at the hood could require additional housekeeping, which measures to be implemented and, depending on the dust, may lead to increased risk of students' exposure to this weld fume or wood dust. So once we design the proper hood to capture the contaminant, the goal is to move this particulate to the filtration system through a series of ducts. A properly designed duct system should pull the minimum airflow required at each hood and maintain velocities required to transport material through the duct and to the collector. And you have to be able to do this utilizing the least amount of energy as possible and minimizing any wear and tear on the duct components. So a few common mistakes that I see when it comes to duct design typically would be the incorrect type of ducting being used, the incorrect duct sizing or fittings being used, and the duct system not being balanced correctly. So the minimum duct velocity, okay, this is a critical design factor when it comes to dust collection. It is the lowest velocity where all contaminant will be transported through the duct. If you go below this velocity, dust could settle out within the duct and cause other issues. So for school wood shops, this is typically between 4,000 and 4,500 feet per minute. And for welding, since it's lighter, the industrial ventilation manuals requires a minimum of 2,000 to 2,500 feet. However, we typically prefer to improve that to commonly around 3,000 to 4,000 feet per minute to keep that velocity up and keep the cost down of the equipment. If the duct velocity is too low, a dust can settle out within the duct and cause problems, such as a safety issue. Imagine the dust collector in ductwork, like shown in this image here, gets too heavy and the ductwork falls. It can ultimately lead to a total system failure. If the duct velocity is too high, it won't create any safety concerns, but it will require more energy to move the duct air through the duct. Ultimately, this could impact the size of the system, fan, as well as create issues such as an increased noise, abrasion, and wear and tear. So again, a critical design factor. So just a few pieces of advice when it comes to duct types. There's rectangular duct, which is commonly used in most HVAC applications, which is moving only clean air. We don't want to use it in industrial applications where dust settles out in the corners. Now, it's okay to use on the clean air side, though, because there is no dust in that airstream. So when specifying industrial duct systems, we want to make sure you call out round, heavy-duty industrial ductwork. Most dust collection applications will use Class 2, 3, and 4 ductwork when designed by SMACLA standards. Typically, the higher class rating of the ductwork, the heavier the gauge. Now, spiral duct tends to leak air and could impact your system airflow design by about 10%. And of course, if put outside, this could also prove a prime source for water to enter into the ductwork and get into your dust collection system. So spiral duct is really not recommended. The other type of duct is flexible ductwork. It's very popular because it allows students to modify the physical hood location to fit their process. However, it comes at a price. Because there isn't a smooth inner surface on the inside of the dust, as the air flows through it, it creates a ton of turbulence and therefore requires significantly more energy than traditional hard ductwork. So if you're going to specify flexible ducting, we recommend minimizing it as much as possible, because flexible ductwork can be 2 to 3 times or 4 times the resistance as standard straight pipe pumps. Oh, so my last piece of advice about ductwork, which is very critical, is avoid T's and 90-degree angles. If your elbows are mitered 90-degree turns, all the air has to slow down, it has to turn, and then speed back up. And the same with branch fittings at a T fitting creates a ton of turbulence as air coming into it as a 90-degree angle. And turbulence equals more than energy consumption and higher static pressure. So when you're designing the system, it is important to select options that minimize turbulence within the duct and avoid things like T's and 90s. 30-degree and 45-degree branch entries are recommended, and we also recommend putting the branch entry into the transition piece, which is shown above in the branch fittings. So moving on, as I mentioned earlier, that having an unbalanced system is something that can go wrong with duct design. So when customers add new equipment to an existing system, they often don't consider the impact it will have on other existing equipment. In most cases, existing systems aren't modified to accommodate the additional airflow or static, and thus it becomes unbalanced. Luckily, if you know a school is going to be expanding their process, there are ways to design future lines into the system so they don't have to sacrifice performance. Our next component is going to be the dust collector.
Hey, Dave, I'm sorry to interrupt you. I'll give you a second to get a sip of water here. Just a reminder to everyone, I see a couple questions have come through the chat box. You can put in your questions as you think of them throughout the slideshows.
All right, thank you, Ashley. The main objective of the dust collector is to deliver significant efficiency while operating in a predictable, stable, and economic fashion. The most common mistakes that you could do wrong, as we see when it comes to collector design, are the wrong filter technology, incorrect sizing of the collector, either too aggressive or too conservative, or a poor installation, inlet orientation or fan locations, creating airflow and dust distribution problems within the collector. Now, the picture above up there is a project that I did, which you can see it's a 16 cartridge unit. This is handling 8,000 CFM at Pittsville High School in Wisconsin on a welding shop. You can see the platform ladder in front to service the filters there with that platform. The fan you can see is located to the right with the silencer pointing up. And underneath it, you really can't see it that well, but in this case, it's a sealed drum cover kit with a 55-gallon drum discharge underneath it. So when it comes to school weld shops, the most common will be the portable collector, like the Easy Trunk, the ambient collector, like the DFA, and collection and cartridge collectors like the DFE, shown in the pictures there. When it comes to school wood shops, the most common would be a small bag house like a Unimaster, shown there, or a Cyclone, or like on the right, the DFE again, which is one collector that can be used both in wood and weld shops. Now, we aren't limited to just these. These are just a few that we see in schools the most often. Sometimes we run across oddball stuff, which we have over 30 different collectors that we can use to help. Now, looking at that first collector, the first collector we often see in schools is the Easy Trunk fume collector, which can be used for welding programs. As you can see there, it's on casters and portable. It's conveniently used and moved around in the facility very easily. It's only 28 inches wide, so it fits easily through the doorways. And it's super easy to pulse clean the filters. Now, weld.com made a welding video recently, and they used an Easy Trunk. I'm going to show you a little clip so you can see how it works.
Until we get it right. Until we get it right. Until we get it right. Until we get it right.
So you can see in that video, the placement of the arm is critical, not being too close to generate and suck up the sparks, but far enough away to collect the smoke. All right, so moving on. Now, the part I like. The Downflow Evolution, or DFE, is a cartridge collector, and again, commonly used in both wood and weld shops. It utilizes downflow air movement, which produces superior performance and collects that used horizontal airflow. It has a proprietary cleaning system that minimizes energy loss by focusing on the air cleaning exact path and delivering uniform cleaning energy to all the effective filtration media. The DFE utilizes triangle shaped filters with ultraweb nanofiber technology for improved filtration capacity. And the filter access design makes the changing filters much faster and easier. Customers love it because of its small size, and it means a lower initial purchase prices. The next one on there is our downflow ambient, or DFA. Now this is a little different, that it's an ambient collector, not a source collector. So it doesn't use ductworks or hoods. Instead, it's designed to collect fume from the welding field as they rise. It returns that filtered air near the floor level to assist with air recirculation. It is a tall tower type collector, which means it doesn't take up much floor space. The fan is integrated, so it is completely self-contained. It's also really easy in terms of maintenance and installation, and it uses the same type of cartridge filters as the DFE. For large facilities, multiple collectors are strategically placed throughout the collector to create a racetrack effect of air movement. Oh, in terms of cartridge media, it is important that we select the best option for your specific application. There are a few that we see most in schools, typically the UltraWeb media or UltraWeb FR for flame process stuff. But it is important that we understand the specific process that you are in dealing with so we can make and recommend the best filters for your application. Now, the Unimaster. It's a self-contained with everything needed to begin collecting for a wood shop dust collector. The fan and motor are there. There's an automatic shaker, a shaker motor, and system controls. The installation is quick and easy. It is compact, so it doesn't take up a lot of floor space, but it is intermittent duty. It needs to shut off to clean. Here's a picture of Unimaster outside of a school for a wood shop. For a wood shop. We also have a variety of options for filters in the Unimaster. There's woven polyester, there's polyester anti-static, there's polypropylene, just a few of them that I mentioned. It is an accordion style filter that seats into the filter once you take off the strap there, so it's self-seating. Now, moving on to the Cyclone. The next collector, Cyclones, which can be used also in wood shops. It is a mechanical separator. It uses centrifugal force to remove large and high volume dust. Heavy duty construction, long life, and low maintenance. It can also be used along with optional filter bag assembly, which is shown in the picture here. Economical, it costs less than the other dust collectors, and it takes applications from 300 up to 13,000 CFM with Cyclones. Getting back to the cartridge filtration, here's an example of how I used a DFE collector for a wood shop this was on, and a Cyclone collector next to it was also on a wood shop, but it was for rafters and large dust. We could use a Cyclone to separate that versus having the fine dust and sanding dust with the DFE on the other part of the process. This is one of the projects I did at Seymour High School, about 3,500 CFM, and of course this dust in the wood shop was combustible. As you can see, there's an airlock underneath isolating that from the 55-gallon drum underneath that. And we'll get into the idea of the explosion isolation devices shortly. So when designing a system, the very last thing I think about after completing all the airflow calculations is selecting the size of the fan. The fan is the heart and soul of local exhaust ventilation system. It generates the airflow and the static pressure. It has two responsibilities. First, the fan must deliver the necessary volume or flow required and static pressure to drive the operation of the system. And since many dust collectors can operate with clean and dirty filters, they require airflow often has to be maintained over a range of static pressures. And secondly, the fan you select must be able to deliver the desired static pressure and airflow with the appropriate energy efficiency and acceptable sound levels. For example, non-material handling fan located in the clean air side of the collector are more efficient than material handling fans on the dirty air side of the collector, blowing air into the collector instead of drawing air through the collector. Fan challenges generally fall into two categories, either poor fan selection and a poor fan installation. Like I was talking about, a critical component to fan design is static pressure. It's basically resistance that the airflow must overcome due to system components. It's expressed in inches of water gauge, as you see here. When we design a system, we calculate the total system static pressure so that we can size the fan properly. Now, here's an example. One thing I'm going to run through here. We have a hood that totaled 1.5 inches of friction loss in the application. The ductwork, including straight runs, duct elbows, branch entries, was 2.5 inches. The filter in the collector totaled 6 inches with dirty filters. And the filter to fan ducting was about 1 inch. And in this application, we had a spark cooler on it to reduce for dust mitigation. And that added another inch to it. So the total system static pressure for this particular project was 12 inches of water gauge. So fans are sized based on system total static pressure and the required airflows. For the example I just brought up, let's say that we need to size a fan for the example, which is 12 inches of water gauge and say at 9,000 CFM. We use a system static pressure of 12 inches and line it up with the airflow, 9,000 CFM. And when these two lines intersect, we land on the backward inclined fan between the TBI 25 and the TBI 30. So we go to the fan curve to the right of where it lands. Since it is rare that we land on the curve, in this case, it would select the TBI 30. See how the static pressure is so important? Actually, this application at 9,000 CFM can be achieved by 3 different fan selections, the 20, 25, and 30, but the static pressure design drives the horsepower. Always err on the side of conservative. If you have too much air, you can damper it back. If you don't have enough, there's nothing you can do. Okay, to finish things up and then open this thing up for questions, there are a few other design considerations to think about. The first one is the total cost of ownership for a school's dust collection system. An example of total cost of ownership for a dust collection system is, say, how much energy is required to operate it? Where is the unit coming from? I mean, how easy is it going to be to get parts? Say, how long do the filters last? And how easy it is to change and maintain the filters? And what is the life expectancy of a system? Another consideration I wanted to mention is how technology is being used to monitor dust collection systems. We have smart technology all around these days, from TVs to toasters. Now, Donaldson has developed a device called the IQ to make dust collectors smart. This device generates important process data in real time, creates automatic alerts and historical reports, and is available to customers at no charge. It's a great way for schools to maintain and manage and track regulatory compliance and information and troubleshoot the dust collector to make it more efficient. And regulatory considerations, everyone's favorite. Each of these agencies have design expectation to produce process-related hazards. And as everybody knows, they aren't always consistent with each other. Knowing the hazard related to the process, the system designed to handle will ensure that you and the school to make sure some critical design discussion up front in the process. It can be very expensive and time consuming to change the design once the equipment is installed and in operation. Okay, speaking on NFPA, I told you I'd bring that back into this conversation. Now, it is a global, self-funded, nonprofit organization devoted to eliminating death, injury, property, and economic loss due to fires, electrical, and related hazards. Standards developed by NFPA are also called consensus standards because they are widely recognized by authorities. NFPA standards are referenced in national and international fire and mechanical codes, which are adopted by many states and municipalities. And if so, local building inspectors and fire marshals may be required to enforce NFPA standards. OSHA also considers NFPA standards to be good engineering practices, and during a general safety inspection may reference NFPA standards when issues or fines of the facilities are being generated. This is another job, a recent job I did, another wood shop in Wisconsin. This project was in Dodgeland in Juneau, Wisconsin, a filter cartridge unit handling 5,000 CFM. Now, as you can see, the dust was combustible, as I talked about before, and part of the mitigation strategies, they went with inlet and outlet isolation and explosion and dust discharge isolation, all shown in this picture. Now, I got a question for you. Has anyone designed systems yet with explosion isolation mitigation? If you have, give me a thumbs up. If you haven't, give me a thumbs down. What do we got, Ashley?
All right, they're coming in. We got some thumbs up, some thumbs down, a little bit of mix of both, it looks like.
This part, you'll have more and more combustible dust mitigation practices you'll have to deal with in the industry these days. You wouldn't believe it. The only thing that's probably not combustible is rock. Everything else particularly has a KST value to it and will require some type of combustible dust mitigation. Like I said in this picture here, the red device, the closest device to you in that rectangular ductwork, which is clean ductwork, is a high-speed abort gate, which doesn't allow the flame or any type of combustible dust to go back in the building. The device to the right of that is a isolation device that is a non-return valve, as it's called, an explosion isolation device, that if there's an explosion in the dust collector, it keeps that explosion in the dust collector and allows the explosion vent, which you can see in that silver rectangular thing on the side of the dust collector, to prevent that explosion exterior from the building, away from everybody, away from all the operators. And of course, underneath, the weakest point in the system would be the underneath, if you had just flex hose of the 55-gallon drums. So we have, on this one, we have a rotary airlock, which isolates that explosion again, keeps it and lets the explosion vent vent it. We also have sealed drum cover kits available for other things, which I think I'm going to go on. So with that, I'm going to wrap it up with talking a little bit about NFPA. NFPA 652 is the most broadly applicable standard. It provides the basic principles and requirements for identifying and managing the fire and explosion hazards of combustible dust and particulate solids. NFPA 652 is a starting point for the process owners. Within it, there is a flow chart that directs process owners to various industrial specific standards. Here's that list of all the current industrial specific NFPA standards, a few of which may apply to school wood or weld shops, such as 484, standard for combustible metals, and 664, standard for prevention fires and explosion in wood process and woodworking facilities. If the process owner doesn't fall into one of these industry specific standards, then NFPA 654 applies. Now, trust me, this is a complex, as ever, changing topic, which is why we have multiple combustible dust experts at our Donaldson team to help you. Now, when it comes to mitigation, combustible dust risk, it falls into two main categories. There's prevention and there's protection. Prevention mitigation strategies involve reducing the likelihood of an event to a more tolerable level. Since prevention may not always be successful, protection is all about limiting the severity or consequence of the event to a tolerable level. Here are some items that we have. Inlet and outlet isolation. The dust collector must be isolated from the dust collector from the event of a deflagration in order to keep the event from spreading back into the process or returning into the area, which I talked about on the previous slide. Now, the deflagration isolation, or DFE collectors, was independently tested, and the filters successfully isolated the deflagration and allowed no flame or sparks to pass into the clean air plenum. This is important when considering when returning airflow back into your facility. It may minimize or reduce a high-speed abort gate coming back into the building. And hopper isolation, which I showed you, typically the rotary airlock or specifically designed drum to prevent explosion from propagating through the dust collector hopper outlet. Now, and explosion venting of outdoor units and chemical suppression for indoor units to minimize or eliminate damage to the dust collector from an explosion before it becomes catastrophic. There is also indoor flameless venting also. Designing a dust collection system for schools can be complicated, and there's a lot that goes into it. But that's what we're here for. We sold countless of dust collection systems around the world and have local support in your market, and we're here to help.
Thank you, Dave. We're going to finish up with some Q&A. Dave, you can turn your camera back on. Just a heads up to everyone that has attended, you will receive an email that includes your CE credits. We also will make sure to get you a link to the recording session today. We're going to be putting the link in the chat box for you to get to our webinar page, which includes a few different recorded webinars and a form to fill out if you're interested in an in-person lunch and learn or a customized webinar for your team. All right, so we're going to start with the first question here. Who is responsible for providing the dust mitigation plan?
The dust mitigation plan is usually regulated by the entity or the authority having jurisdiction. Anytime a dust is combustible, you can either accept it as combustible and put the proper mitigation in there, or you can have the dust sent out for analysis and figure out how combustible it is and have the right proper KSD value associated with the components that you're going to put on there. So it's the governing body that dictates if they do or don't have to address that issue. Authority having jurisdiction, if you want to call it.
Yep. Next one here is, can you discuss the significant difference in capture versus conveying velocities?
Well, capture velocity is how we get it into the hoods. That's the dust that's out in the air, that's sitting out there. You're trying to get it into the ductwork. That's what you use the capture efficiency for. That distance of capture efficiency is critical because if you get it closer, you don't require as much airflow to get it into the ductwork. Once you get it into the ductwork, now you got conveying velocity. The conveying velocity takes it from point A to point B, from the hood to the dust collector. And you don't want the dust to settle out in there. So the conveying velocity is a lot higher than the capture velocity.
Okay. Next one here is, can dampers be used to balance the system?
That's a good question. Per NFPA, they do not like dampers, but there are a lot of schools out there that still do dampers designed to balance it out. That's more recommended by putting plates in there or the duct diameters being smaller to kind of balance out the system. Because what happens is if there's a damper in there, it's a low velocity spot right behind it typically. And if dust can settle out in there, it can become a fire hazard. So that's the concern that people have out there. So if guys come out from NFPA, a lot of them will say that we can't have dampers in there, but there are a lot of them out there. If anything, maybe a butterfly damper instead of a knife gate damper, because it doesn't, it opens both sides of the pipe and allows air to flow through there.
Okay, and so since we're on balance, there's another question that says, is the ductwork self-balancing?
By itself, no. You have to add distances in it or create smaller diameters to get it to be the same resistance as the other branches that are out there. So it'll try to, air is lazy. Air will take the least path of resistance. So if there's a big diameter opening closer to the dust collector, you'll have the majority of air going into there. So you'd have to damper that back to get airflow out in the further collection point. So if you make that connection point smaller, closer to the dust collector, it adds more resistance to it and it'll help balance out your system in the long term.
And then it says, another one I'm balancing here. It says, are balancing devices allowed in dust collection system designs like blast gates?
I think that was similar to the other question that we just brought up, that blast gates are not recommended as knife gates in there because of the combustible dust, or the dust being able to settle out behind them, and potentially having a fuel that's in the ductwork that if a fire did occur could burn it there. So yeah, I think that's pretty much the same as the last question or one of the other questions.
Yep. Does exterior ductwork need to be insulated?
Good question. It could be, and a lot of schools are insulating it. If you get in a dust collection system that you're turning on in the morning and there is no insulation on it, of course you'll have some condensation that'll be created there because the warm air coming out of the building will be going through the ductwork. So it could be an issue. So a lot of them do insulate them. If they're not insulated, I recommend turning them on maybe a half hour prior to starting up the system to get the collector up to temperature and get the moisture out of there before you start running dust and product into the dust collector, which could get sticky and tacky and hence maybe bridge over your hopper or cause some other problems with it. But yeah, I'd say probably 80% of the schools are insulating all their ductwork outside now.
All right, the next one's based on the pictures. So it says, in some of the pictures of the commissioned units, what is the black cone shaped thing that's in the duct before some of the dust collectors?
Before some of the dust collectors will be spark coolers. Those are devices that are put in line, which basically takes the ember that's coming through, which would be a spark, and it accelerates it and decelerates it by expanding it out and then coming back to the same diameter ductwork, taking all the energy out of it, therefore, reducing the potential for that staying hot and being transported to the dust collector and causing a fire somewhere downstream. But yeah, they're usually, I think a lot of them are black, but it's like a little device that it'd be 8-inch, it'll expand out to 12-inch, then back to 8-inch. That's normally a spark cooler.
Next one here is it permissible to recirculate the portable weld exhaust into space?
Yes, it is. I would recommend putting a safety filter on it or a final filter, whatever you want to call it. Your filters are 99.9% efficient on 0.3 to 0.5 micron particulate. It should remove all the particulate or 99.9% of it. But if there's a failure in your filter, you want to minimize that from getting back into the building. So putting a safety device after it to collect it if there's a filter failure, because if there's embers going in there, you might have little pinholes in the filters and fume can get through them. Then it's coming back in the building and creating a bigger issue. So I'd say, yes, you can bring it back in, but I would probably put a HEPA or an ASHRAE type of safety filter on it, if you want to call it.
All right, so the next one's pretty long, Dave. So I'm going to try to say it and then can you me repeat it if I can, okay?
Yep.
It says, can you talk about the means and methods to interlock the dust collection system with the dust producing equipment? This is a CMC code requirement. I've considered two approaches. Each dust producing equipment needs to relay it to enable the dust collector. Number two is dust collector is enabled, which allows power to the electrical panel that powers the dust producing equipment. Are there output relays on Donaldson equipment to interlock to the makeup air unit?
That's a very good question, and I'm dealing with it right today with a couple school jobs that I have. And yes, we can put control relays in our controls that would have a signal that would be fed from the makeup air unit that has to engage that contact for the dust collector to be turned on. There's also end switches that we put on dampers in lines that make sure the dampers opened or closed when they turn on or off the dust collector. That is actually a critical device. And the other part is your explosion mitigation items. Those would feed back to some central control panel that would deactivate the dust collector and disengage everything that you needed to if the occurrence of an event did happen. If you had an explosion or you had a fire in the dust collector, you don't want it to continue to run and continue to fuel that fire with more oxygen. So you want to shut the dust collector off. You can shut off the compressed air. You can do as much or as little as you want to. But yes, those devices would actuate with the control panel to shut and turn everything off. And then sequencing to turn on, opening up a damper outside before the dust collector turns on so you don't collapse ductwork. So yes, we can build that into the controls. That's an electrical control function of the system. So you need to discuss with your territorial manager or the guy that you're working with, to your dealer, to get the equipment and make sure they have all those components integrated into that panel. I do that quite a bit with a lot of these schools that I've worked with recently. They want to know if the makeup air system's on before the dust collector turns on. So yes, there are means of doing that, but it's electrically controlling it.
Thank you. Next one here is what are the application advantages and disadvantages of baghouse filters versus cartridge filters?
Okay, baghouse filters. Baghouse are efficient per volume. Cartridges are efficient per efficiency. That's the main thing I would consider with deciding a bag versus a cartridge. A cartridge is 99.9% efficient at 0.3 to 0.5 micron. A bag is 99% efficient by volume. So a bag depth loads, draws the product into it in depth loads, where a cartridge surface loads allows you to pulse clean off. Even a pulse cleaning baghouse allows you to pulse clean off better if the product surface loads. So that's your main concern. The size of the particulate also is determinant on which collector you would use. If you have product that is very large, say 50 to 75 to 100 micron in size and larger, a bag can handle that very well and give you a little bit more forgiveness if there's moisture in the air process than a cartridge would. But definitely a cartridge is for smoke and fume, very, very fine wood dust. I would go with cartridge filtration. If you got just basically chop saws and stuff running, you could use a baghouse or a cyclone on that. So I hope that answers your question there. But yes, size and particulate does matter when it comes to bags. Bags handle larger size dust than cartridges with finer dust.
All right, next one here is it says, I'm seeing many school systems using smaller combination programs using in conjunction with each other, such as a marker space. These spaces will commonly have welding, grinding, CNC, and 3D printers. They use steel, aluminum, and plastics. What products are recommended?
If you're talking fume, I think he's talking fume in there, wasn't he, Ashley? Or what they're dealing with is fume still. So
Yeah,
if you're getting,
fume from welding, grinding, CNC, and 3D printers.
yeah, that would be smoke. That would be submicron. You definitely want to go with a cartridge collector on that application than a baghouse or a cyclone or anything else. Yes, most definitely cartridge on a fume that's being generated because it'll take care of it.
Okay. Next one here is what about using a sealed drum kit in lieu of a rotary airlock with 55-gallon drums?
Awesome. I love that question. Yes, you can. You have to have the authority, the AHJ authority having jurisdiction, understand that it will stop the flame propagation and it will not release through there, but they have to realize it's not a rotary airlock. You do have to consider one thing with that. Now you have a sealed drum cover kit. There's a bigger distance, the L to D ratio, when it comes to explosion venting. That takes a larger distance there because the 55-gallon drum is all part of the dirty air plenum. So we got to make sure that we properly size that we have enough vent space for it. But yes, a sealed drum cover kit is a very economical way to go. It's a 55-gallon drum under there. The only time I see a little different is if you're generating a lot of dust. The 55-gallon drum may not be large enough for your school wood shop when they're doing planing and stuff. It could fill up in a half hour and you got to dump the barrel all the time. So then they'll put airlocks underneath them with dumpsters or something like that. But yeah, sealed drum cover can be used. Not a problem. Just make sure your authority having jurisdiction is okay with it. And we can provide documentation of what we claim with our flame propagation on it. So we should be good.
All right, Dave. We do have a question around IQ and the capabilities of it speaking to BACnet, and I'll actually answer that. So if you, whoever asked this question, we do have the ability to tie into central systems. If you have specific questions on this, please send me an email and I will get you to the correct people because each different system, it works differently to tie into that connected solution. And the next one we have here is, are there examples of portable wood dust collectors?
Portable wood dust collectors. I have not seen many of them. The other things we could use would be smaller DFEs that can handle lower air volumes because portable usually means less than 1,000 or 1,500 CFM for them. Like the Easy Trunk is 780 CFM. It's 800 CFM for weld fume, but weld fume doesn't generate a lot of particulates, so it doesn't need a lot of storage space for the dust. So when you jump into a portable wood dust collector, you might be able to do it with a DFE, smaller DFE that could be either a cabinet base or a DFEP Pro 2 to 1,000 CFM there, with it dumping into maybe a 5-gallon or 25-gallon container underneath it, so you can handle volume of particulates that's coming out of there. That's the main concern, to be able to handle the dust that you're collecting in with a portable collector.
All right.
I would say ask your territorial manager, your dealer. We can come up with something. We got solutions for a lot of different things.
All right. Next one here says, looks like a concrete slab is required for external units. Any specific requirements for that slab?
That would be the local building inspector, someone that would regulate what they do and don't need to do. I normally would put them with pylons or footings that would go down below the frost line with concrete above it. And again, some people recommend 6 inches, some see they need 8 or 10 inches. A lot of that's locally regulated by the local jurisdictional area that it's covering. But I would say if you have a collector with footings under each of the legs that go down below the frost line and concrete with maybe 4 to 6 inches on top of it, just to be able to get the drum off there, you should be fine. But again, I'm not the one that can tell you yes or no. Your local authority would have to do that for you.
All right. The next one is it permissible to recirculate? Oh, we already did that one. Sorry. Was a secondary question. With the rise of the popularity of the laser welding and the fume and the particulate generation by the process, are there any specific requirements one needs to take into consideration when designing the system, or will the normal Donaldson filters be adequate to capture the fume and particulate?
The normal filters will capture the particulate and the fume, but these lasers are running a lot faster and they're cutting a lot thicker material. That would be the concern I would have, because if you're cutting 1.5 inch, 2 inch plate steel, you're throwing a lot more dust at the dust collector. The CFM may be the same in the table, but the loading on the dust collector is going to be that much higher, which would cut down in your filter life. So you would derate the collector or make the collector larger to handle fast, thick cut metal, with the laser technology that's out there now. So it would work, but the filter life would not be as good with our standard practices in wood shops and school shops. They're only running 5-6 hours a day. If you're talking an industrial application, then you got a problem, because they may run 16 hours a day, throwing a ton of dust at the dust collector, which it just can't handle that loading characteristic. So again, the territorial manager or your dealer can walk through that with you, knowing the conditions that you're dealing with on that application, and become application specific and select the right collector for you to give the right cost of ownership for it. That's the main thing.
Okay. What about diversity where they don't intend to use all the processes at the same time? How do you maintain the velocity?
Well, you have to shut off ductwork where it's not being utilized. That's a hard scenario to fix, because like you say, when you're turning on and off process points, it's a problem because conveying velocity will drop in the bigger diameter ductworks. You have to basically have a minimum duct CFM to maintain a minimum duct velocity in the largest pipe diameter. That's the big thing. It may require you to put smaller ductwork in there, which may require more energy, but it will still keep the conveying velocity up, and you'll never have your ductwork fail or fall down or fill up and have a chance to hurt someone in your process. So that's a tough one to deal with when you're doing turning on and off duct pipes. A lot of times they'll run a plenum that'll be a single diameter 6-inch pipe, and they got to have 2 or 3 of the openings always open to maintain that velocity in the ductwork. But if they have them all open, it should really be a 10-inch, but they don't have the CFM to do that. So the static pressure is critical when you come to it. So you may be more energy to run it through a smaller pipe, but to keep the velocity up, which is more critical.
All right, we're going to go to the last question, Dave, here, and then we're going to finish it up. Regarding the dust mitigation plan, you stated that the AHGJ will determine whether or not it is required. If it is required, is the engineer of record responsible for creating the plan, or should an industrial hygienist create the plan? And how often do you see this in dust mitigation plans on projects in California?
Oh, in California, now you're talking a world that I'm not real familiar with, except the regulations are a lot more stringent out there. I do know that. Yeah, for the way I would approach a scenario like that is, if there's a potential for the dust being combustible, is to send it off and have it tested. Okay, you send it off to Falski and such, whoever you want to do, whoever does the testing. They can do a go, no go test on it, fairly inexpensive. If it's go, meaning it is explosive, Then you have an option to do a more thorough test on it and figure out the actual explosibility of the dust to get your KST value. Your KST value dictates the size of your airlocks. So once you know that there's something there, you know you have to do something. We would be able to supply components in the system to protect for that combustible dust process. But yes, you as the design engineering firm would be the one that would have to either sign off on that or have the industrial hygienist sign off on it, or the insurance carrier, whoever, again, the authority having jurisdiction. I hate to keep saying that, but they are the final say in everything if you do or don't need to do something in your process. So I hope that answers your question with not, going around it too much, but that's how you got to deal with it.
Yeah, thank you, Dave. And as we said, we have territory managers across the United States, so don't hesitate to reach out to me. I can get you in touch with the correct person. But thank you all for spending your time today and learning about this dust collection system design. And you will have an email follow up with me. And thank you and have a great day.
Thanks, everybody.